Hi, in this video, I will talk about our paper Connectivity Lower Bounds in Broadcast Congested Clique. This is joint work with Sriram Pemaraju from the University of Iowa. I am Shreyas Pai, and a full version of this paper is available on arXiv in the link on the bottom of the screen. In this paper, we consider the BCC1 model, which stands for the Broadcast Congested Clique model with 1 bit bandwidth. We are given a synchronous all-to-all communication network in this model where the nodes can broadcast 1 bit in each round. The input graph is a subgraph of the communication network, and throughout this presentation, dashed edges will denote network edges only, and the bold edges will denote input graph edges as well as network edges. Each node knows which of its n-1 incident network edges are also input graph edges, and this is how the input graph edges are distributed across the network. Each node has a unique login bit ID, and the nodes want to compute graph properties such as connectivity, where they ask if the input graph is connected or not, and connected components, where they want to compute which component they belong to. Initial knowledge is an important aspect in the BCC1 model. There are two ways one can define it: the KT0 or the port model, where the nodes only know their own ID, and the KT1 model, where the nodes know the IDs of all of the other nodes. We need O of log n rounds to go from KT0 to KT1, where each node will broadcast its ID bit by bit to all of its neighbors. This distinction is not superficial. In fact, we need different lower bound techniques in both of these versions to show lower bounds for different problems. In this paper, we consider the connectivity problem in the BCC1 model. The best known KT0 and KT1 algorithm known in this model runs in log squared n over log n rounds. The best known lower bound for connectivity is log star n rounds. So the question we ask is, can we show better lower bounds for connectivity in the BCC1 model? Our results in this paper, we show that in the KT0 version, there is a randomized omega log n lower bound for connectivity. This holds for constant error probability. And in the KT1 model, we show a deterministic log n lower bound for connectivity as well as a randomized log n lower bound for connected components. Note that a lower bound for connectivity implies a lower bound for connected components, but not vice versa. The techniques that we use in each of these settings are shown here. So in the KT0 model, we use a technique called edge crossings, and in the KT1 model, we use techniques like communication complexity and information theory. Let us talk about the KT0 lower bound in a bit more detail first. Our KT0 lower bound works for the special case of one cycle versus two cycles, which is a special case of connectivity where the input graph is either a single cycle, as shown on the left, or two disjoint cycles, as shown on the right. The algorithm has to distinguish between these two possibilities. We also assume that we are given a consistent orientation in each cycle, that is, each connected component of the input graph. And here we have shown that each cycle is oriented consistently in clockwise direction. The lower bound for the oriented case also implies a lower bound for the non-oriented case. In the KT0 model, the nodes only know their own ID. So ports are used to differentiate the messages received from other nodes. For an edge UV, it is connected to U at port P and to V at port Q. So if U broadcasts a message, it will be sent through port P to V, and V will receive that message through port Q. And this will be consistent throughout the algorithm. So let's define an operation called port preserving crossings, which will be instrumental for proving our KT0 lower bound. Consider two edges, u1 v1 and u2 v2, and we wish to cross them as shown here. Now, we also need to worry about the network edges that are between u1 v1 and u2 v2, that is u1 v2 and u2 v1. So we take the two bold edges and we cross them as we wanted, and the two network edges now need to be crossed as shown here. So we get one instance shown on the left, and we perform the port preserving crossing operation, and we get the instance shown on the right. Let us ignore the dashed edges for simplicity, and if we flip the edge u2 v2 to be v2 u2, then the port preserving crossing operation looks as follows. It will result in the instance on the right. So we can see that by using port preserving crossings, we can go from a one cycle instance to a two cycle instance interchangeably. That is, if we take the edge u1 v1 and u2 v2 in the sixth cycle and perform the port preserving crossing operation, we will get the two triangles instance on the right. And notice that if u1 and u2 send the same messages throughout the execution of the algorithm, and v1 and v2 also send the same messages throughout the execution of the algorithm, these two instances are indistinguishable. This leads directly to a deterministic lower bound by observing that in each round at least half the nodes broadcast the same bit. This means that a constant fraction of edges can be safely crossed so that the crossing leads to indistinguishable instances. By performing a port preserving crossing on these edges, we get a one cycle instance and a two cycle instance that are indistinguishable from each other. We will run out of edges to cross only after omega log n rounds, because in each round at least a constant fraction of edges can be safely crossed. And this gives us a deterministic lower bound, but extending this deterministic lower bound to randomized algorithms is the main technical challenge. So going towards a randomized lower bound, we use Yau's theorem to prove a randomized lower bound. It decomposes the task of proving a randomized lower bound to designing a hard distribution mu over the input, and then showing a deterministic lower bound on inputs that are sampled from this hard distribution. So to show a randomized lower bound, we need to show that a large fraction of instance pairs according to mu are indistinguishable. To do this, we introduce a combinatorial structure called the indistinguishability graph. In the indistinguishability graph, we have the set V1 of one cycle instances on n vertices and the set V2 of two cycle instances on n vertices. An instance I1, that is a one cycle instance, has an edge to an instance I2 in V2 if the two instances are indistinguishable. We show that this is a bipartite graph with size of V2 equals to size of V1 times O of log n. And the candidate hard distribution that we use is that we put a probability mass of half over all the instances in V1 and a probability mass of half on all the instances in V2. And since the sizes are related as shown in the first bullet point, the instance I1 will have logarithmically more probability mass than the probability mass on instance I2. Initially, each one cycle instance will have O of n squared neighbors in the indistinguishability graph. In each round of the BCC1 algorithm, the number of these incident edges falls by a constant factor, by the same argument that we used in the deterministic case. So after some logarithmic number of rounds, the degree of each one cycle instance falls down to something like n to the 1.6. The crucial result that we show is that for any set S of one cycle instances, the size of the neighborhood of S is at least log n times the size of S. This looks like the precondition for Hall's theorem, but a little bit stronger. And in fact, we use polygamous Hall's theorem to show that each instance in V1 can be matched with O of log n unique instances in V2. This polygamous Hall's theorem is essentially O of log n separate applications of the normal Hall's theorem that we know. So a T-round algorithm either errs on a one-cycle instance or on the log n matched two-cycle instances because all of them are indistinguishable after T rounds. So any algorithm that runs for less than T rounds will err on at least a constant fraction of instances according to mu, because the blue one cycle instances have logarithmically more probability mass than each orange two cycle instance according to the Hart distribution. So this gives us a KT0 lower bound for any randomized constant error algorithm of omega log n rounds for the connectivity problem. Now we move on to the KT1 lower bound. In the KT1 model, the nodes know the IDs of all of their neighbors, and we can think of this as the port numbers being exactly the same as the ID of the neighbor that it connects to. In this case, we cannot play any edge crossing tricks precisely because the port numbers and the IDs have a one-to-one correspondence. In fact, no edge crossings can be port preserving. We need different technique, and here in this case we use two-party communication complexity reductions. In the two-party communication complexity setting, we have two parties, Alice and Bob. Alice is given a private input X and Bob is given a private input Y, and they both need to compute the value of a certain joint function of f of x and y. Take equality as an example. Alice and Bob get private inputs x and y, which are n-bit strings, and they want to find is x equal to y. A trivial protocol for the equality problem is Alice takes her input x, sends it over to Bob. Bob computes whether x equals y and sends the answer back to Alice. This protocol takes n plus 1 bits of communication. We want to use two-party reductions to show BCC1 lower bounds. The way we do it is by reducing connectivity in the BCC1 model to computing some function f of x, y in the two-party communication complexity setting. So Alice and Bob get private inputs x and y. They will construct an all-to-all communication network along with an input graph using their private inputs x and y, such that Alice will simulate the blue vertices and Bob will simulate the red vertices in the network. Then they run a T-round BCC1 algorithm such that at the end of the algorithm they will know the value of f of x, y by computing the output of each node that it hosts, along with the messages received from the other party. This gives us that a BCC1 lower bound is at least the communication complexity of f divided by n rounds, because in order to simulate each round of the BCC1 algorithm, Alice and Bob need to exchange n bits that were broadcast by each of the nodes in the network. Two-party reductions to set disjointness have been used to show lower bounds for subgraph detection in the BCC1 model by Drucker, Kuhn, and Oshman. These include omega n lower bounds for detecting cliques of size greater than 4 and omega square root n lower bound for detecting complete bipartite graphs. Connectivity, on the other hand, is a much easier problem in comparison since it can be solved in log squared n over log n rounds, exponentially faster. And in fact, reductions to set disjointness don't quite work out in the case of connectivity for showing logarithmic lower bounds. So, what is a candidate hard problem that we can use? The problem that we use in this paper is what I call the perfect matching problem. In the perfect matching problem, Alice is given a blue perfect matching and Bob is given a red perfect matching on the same set of vertices. Their goal is to find if the graph with red and blue edges is connected or not. We show in this paper, using techniques from the paper by Hajnal, Mas, and Turan, that the deterministic communication complexity of the perfect matching problem is omega n log n bits. And using our reduction to connectivity from the perfect matching problem gives us a deterministic connectivity lower bound in the KT1 BCC1 model of omega log n rounds. Some open problems that I would like to conclude with are: is the randomized communication complexity of the perfect matching problem omega n log n? Can we close the gap for connectivity in BCC1? Currently, the best low upper bound is log squared n over log n, and the best lower bound from our paper is omega log n. So there is a log n over log n factor gap. Thirdly, what can we show for connectivity in the unicast model with 1-bit bandwidth? In the unicast model, the nodes can send different 1-bit messages to each of their neighbors. The best known algorithm for connectivity, and in fact even for MST, takes O of log n rounds. No super constant lower bounds are known in this model, so can we show constant round algorithms in this case? Thank you, and I will see you at the conference.